Welcome to M1. Today we're looking at Chapter 2, Constant Acceleration. Now, before we get into the formulae for constant acceleration, we need to look at the graphs that you need to know and understand. So there's three types. The first one is a displacement time graph. Now, displacement is the letter S and obviously T for time. If you're unsure what displacement is, well, it's essentially distance, but as a vector. Okay, so it has direction. So think of it as distance from a point. So imagine the school you go to is 5 kilometers away. If you go from your home to the school and back, you would have traveled a distance of 10 kilometers. 5 kilometers there, 5 kilometers back. But your displacement would have been 0 because your start point and your end point are the same. Okay, displacement's a vector, so it measures the distance from the start point to the end point. So in that respect, that's what's the real difference between the two. Now, in terms of the graph, the velocity of the graph is the gradient of the graph. So for these, the gradient of this graph is the velocity. So if I have a horizontal graph, then it means that this displacement, this distance, hasn't changed. The distance has stayed the same value while time is changing. So it means that it's stationary. Whatever we're looking at is stationary or not moving. If we have like a straight diagonal line, like this second one, then it means that the distance is increasing at a steady rate. So this means we've got a constant velocity. And the velocity, as I said, is the gradient of the line. If we've got more of a curve like an exponential, this gradient is getting steeper and steeper, therefore the velocity is getting steeper. So the velocity is increasing. Okay, and if the velocity is increasing, it obviously means it is accelerating. Okay, the objects are accelerating. So that's the displacement time graph. Okay, so just to go with that, a couple of obvious things that I have said. So velocity equals the gradient, as the velocity is the rate of change of displacement, hence the gradient, like ds by dt. And then you've got your average velocity is just going to be the total displacement from your starting point divided by time, whereas the average speed would be a total distance travelled divided by time. So the two things are different, so like average velocity would be this total distance travelled divided by time, and in this case the average speed would be the same. But if this line did something like went up and say went down to a point here, then the average speed and the average velocity would now be different. Okay, because the displacement is only this much, whereas in terms of the distance, we travelled up to here and then we travel back to here. So that distance is a lot more. Okay, so there is some differences there. I won't pop them up, but that's the essential stuff that you need to know. Second type of graph is a velocity time graph. So this measures obviously velocity against time. Okay, so time in these ones is always going to be the horizontal axis. Now, looking at a few scenarios for this one. So first, let's talk about the gradient, velocity and time. So if I was to differentiate this, I'll look at the rate of change of velocity, which is my dv by dt. That would be acceleration. Okay, so in this case, the acceleration is equal to the gradient. Okay, that rate of change of velocity. Now, I'm going to need to do this first one with a different color, but on the graph, if I've got a line along that x-axis, then it clearly means that there is no velocity. Okay, so zero velocity would be stationary. So you can see, there is a bit of a difference. If you're looking at the displacement time graph, stationary is a horizontal line, but it can be anywhere. Whereas for the velocity time graph, it obviously has to be at 0. Now, if I draw a horizontal line kind of anywhere, that's now when I've got my constant velocity. So you can see here now that the graphs are different. So this was the displacement time graph. It was just a linear graph, kind of in the form of y equals mx plus c, whereas now it is a horizontal graph. Okay, this means that wherever this value is here, say it's 10, it means that the velocity is 10 all the way along, even when time is changing. So that is my constant velocity. And then finally, kind of matching up with what we've done before, if now I have a not a vertical line, just a diagonal line in the form of y equals mx plus c. Now this is now when my velocity is increasing, or I've got a constant acceleration. So velocity is increasing. Okay, I haven't written down about the acceleration, as I think that's kind of obvious. If the velocity is increasing, it's obviously accelerating. But you can see now the difference for the same thing. So stationary, constant velocity, and when it's accelerating. Okay, now you need to be able to recognize these graphs, okay, when they come up in questions. One additional thing to look at is area under the graph. Okay, so area under my velocity time graph is going to be equal to the distance, or in this case the displacement. And I should clarify this a little bit. So the area under the graph of like a speed time graph is the distance travelled. Now in terms of a velocity time graph, as long as the velocity remains positive, then the area under it is displacement. If it isn't positive, so if you have a negative velocity, then the area under the graph is distance, not displacement. Okay, so you do have to be a little bit careful about that, but for that to happen, obviously the velocity would need to be below the x-axis, so it should be obvious. Now my final type of graph is the acceleration time graph. Now for the acceleration time graph, we don't have to worry about diagonal lines or sloping lines, as these are way beyond the scope of this syllabus. all we need to know is a kind of our three main scenarios. So the first one, I'll do this in black, is if we have it going along the x-axis. Okay, that is obviously when acceleration equals 0. So that is a constant velocity. So it's kind of like linked with these ones down here. The second type of graph we've got is when I've got one kind of up here in the positive, so that is an increasing velocity as we have a positive acceleration, so increasing velocity. And then my last one, as you might have guessed it, is a negative acceleration. So it's decreasing velocity. Okay, and that's essentially what you need to know about our three types of graphs. Now, in this third graph, the area would be the velocity. Okay, so if I was to work out the area, it would be equal to the velocity. But obviously you have to be careful, as some of it might be underneath the axis, some might be above. So you'd need to do it in sections. Okay, so you would do it just for specific sections of your graph where you get that horizontal line without it changing. And while I can't quite remember, to be honest, off the top of my head, whether this is in this M1 syllabus, but it's certainly worth mentioning. If the velocity, if I look at the displacement time graph, if the velocity is the gradient of that, then the velocity is equal to ds by dt. Looking at my second graph, velocity time graph, then the acceleration is the gradient there, so that's equal to dv by dt. Okay, and this is quite nice because what it essentially means is that if you integrate acceleration, you actually get velocity. And if you integrate velocity, you should get displacement. And here's another kind of way of looking at it. Differentiate displacement, you get velocity. Differentiate velocity, you get acceleration. Because we're looking at the gradient of the displacement time graph for velocity, the gradient of this for acceleration. So differentiate, differentiate. And then going backwards is integrating, isn't it? So integrating acceleration, I would get velocity. Therefore, area under the acceleration graph is velocity. Integrating velocity, I get displacement. Therefore, area under the velocity time graph is displacement. Okay, so that's a bit more simplistic and hopefully just helps you out there. Now, I'm not going to do any examples on these graphs. I think they're very straightforward, and you should be able to do it from this information. Obviously, if you do have problems or struggles with this, please, let me know in the comments, and, I'll expand this video to include then some examples and work through questions on the graphs. Also, just before we get into our constant acceleration formula, if you haven't subscribed to my channel so far, please just hit that subscribe button now. Help me out, okay, and maybe help yourself out in the future. Also, if you're in school and any of your friends are finding it difficult or need some help, feel free to point them in the direction of my channel. it would certainly help me out as well. Next, we want to talk about the constant acceleration formulae, more commonly known as SUVAT, and this is just because of the letters we use. So what I'm going to do first is let's go through each letter, make sure everyone knows what each one means. So S is my displacement, U and V are both velocities. U is my initial velocity, whereas V is my final velocity. A is acceleration and T is time. And just going with this, I'm going to pop it up there. Sometimes we do look at acceleration in terms of gravity, things acting under gravity. And for M1, we generally use gravity as being 9.8 meters per second squared. I know in physics you often use 9.81 to go an extra decimal point. Luckily, most of the questions that you will see where gravity is involved, it will often say use or take G to be 9.8 meters per second squared. Okay, so that's kind of everything. In general, we'll be looking at displacement in meters, our two velocities in meters per second, our acceleration meters per second, meters per second squared, and time in seconds. So that is what we'll be using. I can't say this is 100% for every question, but generally, even if it isn't, you'd often change it into these units. In terms of kind of a little diagram to kind of help you out here, and these are the kind of things, you know, I do often draw diagrams in mechanics. I find them useful and in some questions certainly necessary. But here you've got your initial velocity and then the final velocity that your particle or object is moving at. And during all of this, you know, you'll have some sort of constant acceleration. Now, the distance between your start point and your end point is going to be your displacement. Okay, this is because we're going to be moving in a straight line. So that is our displacement. And then finally, this will be our position after t seconds. Okay, so that's just a little diagram to kind of visualize, you know, what we're talking about. Next, going with this as I was talking, I'm going to give you all the formulae in one go here, and then we'll actually go through finding it. So we've got 5 in total. Now, I'm pretty sure those of you who do physics will say that there are 4 formulae, which is kind of true. It was definitely just the 4 that we used when I was in school, and the 5th one really we just used by, it would come up so rarely, you know, if you had a question you just used 2 of the formulae to get the answer. Okay, so here are my 5 formulae. I've kind of just rearranged them in the order we will be working them out, and you know, I'm just going to put what we're missing. So you'd use a formula or formulae based on what information you had and, you know, essentially what you didn't have. So V equals U plus AT, you can see there's no S in there. My second one, you can see contains no acceleration. V squared equals U squared plus 2AS is no time. S equals ut plus a half at squared is no final velocity. And then very similarly, S equals vt minus a half at squared, there's no initial velocity. So these four formulae, you need to know them, and you're also going to need to be able to derive them. Okay, so the first two, my v equals u plus at and s equals u plus v over 2 times t, these can be derived from a velocity time graph. The remaining three come from these formulae. Okay, so as I said, you do need to be able to do this. You could get asked this in an exam. It is in the syllabus for you to know it. So I'll go through it now before we do look at some questions using these formulae. So as I initially said, this first two formulae come from a velocity time graph. So if I start by just getting an idea of a velocity time graph, something like this line, okay, where it's representing the motion of a particle. Because we've got a constant acceleration, okay, it needs to be a straight line, constant acceleration. And let's put some lines on the graph to make it easier. So at the end here, that will be a time t. This start point is going to be when my velocity is 0, so that's quite important, and this top point is my final velocity there. So this is u, and this point here is v. So that is essentially all I need to be able to get my first two formulae. So the first thing we want to do is think about the gradient. Now this gradient is going to be my y distance divided by my x distance. That's what we're looking at, yeah? So gradient of line. Now the y distance will be this distance here, which is v minus u. And that is going to be divided by the horizontal distance, which is from 0 to t, so that's going to be t. Now we already know previously, as we were talking about, the gradient of a velocity time graph is acceleration, it's dv by dt. So acceleration equals v minus u over t. And what I can now do is rearrange this. So at equals v minus u. Take my u to the other side and we get v equals u plus at. And this is my first equation, or formulae I should say. The second one I can get from the area under the graph. So that's the shaded area. So area under the graph, which you can see here is this purple shaded area. Well, it's a trapezium, isn't it? You know, trapezium has the formula A, B, and H, and the area is A plus B over 2 times H. So in this case, my A is this distance here, which is U. My B would be this distance here, which is V, divided by 2 times my height, which is this distance here, which is T. Now, area under the graph of a velocity time graph is the displacement, as long as the velocity is positive in this case, so it is the displacement. So S equals U plus V over 2 multiplied by T. And now we have our first two formulae. So you need to know how to derive these two formulae from this graph. So essentially exactly the steps I've just taken here. Now that we have these, let's go ahead and show you how to get the remaining three formulae. So first we're going to work out v squared equals u squared plus 2as. This has no t, so we want to eliminate t. So from 1, we can see we can get v minus u divided by a, and that will be t. So I've just rearranged it and sub into 2. So s equals u plus v over 2 multiplied by v minus u over a. So what I want to do is first multiply by 2a, so we get 2as is u plus v multiplied by v minus u. So 2as equals, now I'll write this out in full, but you know, not always completely necessary with these types of ones, the difference of two squares, but uv minus u squared plus v squared minus uv. These will obviously cancel. Take my u squared to the other side, and we get v squared equals u squared plus 2as. And this becomes my third formula. Now, if we look at s equals ut plus a half at squared, there's no v. So that means we want to substitute equation 1 straight into equation 2. S equals u plus at times by t divided by 2. So you can see now, if I just add these two together, I get 2u. I got at times t. I'll just put it like this first of all, shall we? So now I've got 2u times by t divided by 2. So it's going to be ut plus, and this one now is at squared. Okay, could have taken an extra step in there. You know, if you want to, you could have then perhaps done the 2ut plus at squared over 2, ut plus a half at squared, or anything kind of along those lines. But that gives us equation, or formula I should say, number 4. And finding my final equation is very much like we did with the last one. So first we want to rearrange 1 to make it u equals. So u equals v minus at, and then sub it into equation 2. So that means I get s equals, now instead of u I've got v minus at plus my v times t over 2. So now you can see that we've got 2v minus at times t over 2, or 2vt minus at squared over 2, which is vt minus a half at squared, or equation 4. And there are all 5 of my equations. Just popping them all back up for you in one go before we head into some examples. Now, in this example, a stone is sliding across a frozen lake in a straight line. So I want to do a little quick diagram just to put this information on. It's not necessary in all questions, but it often can be useful. So we've got a stone sliding across a frozen lane in a straight line. So u is equal to 12 meters per second. The acceleration is going in the opposite direction. So what we want to do is we always want to kind of give one direction as the positive direction we're going to use. So I'm going to use left to right as positive, therefore my acceleration will be a negative 0.8 meters per second squared. And if I'm thinking about the total distance the stone travelled, well, it's slowing down, so the total distance will be when the velocity equals 0. And at this point, I don't know the time, and I don't know, obviously, the distance, which is what we want to find. So what I'm looking at here is we know u, well, let's put them down. U is 12, v is 0, a is minus 0.8. We actually want to find s, and we could find t, we don't need to. So when I look at this, I go, right, we got u, v, a, and we want to find s. So no t. No t is v equals u squared plus 2as. So v is 0, so 0 squared 0, that's equal to 12 squared plus 2 times minus 0.8 s. So I'm going to multiply out my bracket and take it to the right. So 0.8 times 2 is 1.6. S is equal to 144. Therefore, S is 90 meters. Now we want to find the speed of the stone at the instant it had travelled half of this distance. So in this case, u is still 12, v is what we actually want to find. The acceleration is still the same as its constant, and this time s would be equal to 45, half of that distance. So now I'm looking at u, v, a and s, so it's the same formula, isn't it? So v squared equals u squared plus 2as. So v squared equals 12 squared plus 2 times minus 0.8 times 45. So v squared equals 72. That means that v would be equal to 6 root 2 or 8.5 meters per second. This is the two significant figures here, or 8.49. Did it to 3 significant figures. Okay, and that's an example of what you need to do. You just put a sketch down where appropriate. Sometimes it's a bit too obvious. This one's quite an obvious one. I don't really need a sketch, but a lot of them where there's more steps can be really useful. And also put down your SUVET values that you know and what you don't know. Okay, because you need, well, basically you're going to need 3 values, aren't you, plus 1 to find to use any of the formulae. Now, this second example here is one under gravity. So first we want to start off with a little diagram, and we've got a ball that is thrown. So ball A is thrown 46 meters above the ground. So thrown from a tower directly down, so UA equals 5 meters per second. Ball B is thrown directly up, so UB equals 18 meters per second. And obviously somewhere they collide. We need to find that distance, and we need to find that distance from here where A was thrown. So let's look at ball A. We'll take downwards as the positive. So we know that U is 5. Acceleration is gravity, going in the same direction. V we don't know, T we obviously don't know, and S we don't know. Now, we're not worried about V, okay, the velocity they hit each other. We obviously want to eventually find S, but when I'm thinking of the two balls, their S values are going to be different, aren't they? Because one is going to travel a distance or displacement from the top, the other one's going from the bottom. T is my key thing here that I want to first initially work out. Okay, but let's put that S back in there because we need something in terms of S as well, don't we? So S equals ut plus a half at squared. So S is equal to 5t plus a half gt squared. And this is the distance that A has travelled. Let's look at ball B. Now ball B I'm going to take positive as going up. So U is going to be 18, where the acceleration is now negative g. Time t we don't know, but same as the other one. And S, let's put that as SB, which will mean that I'll change this one to SA. Whereas in terms of the times, both my times are going to be equal to each other. So I can put them both as t, they're the same t. So S equals ut plus a half at squared. Remember, as always, write the formulas down every time you use it. Every time you're using it and you're writing it down, it's just giving your brain more chance of remembering it, which is a good thing. So here we have 18t plus a half times minus gt squared. So we've got 18t minus a half gt squared for SB. So we've got two pieces of information here. We've got, at the moment, three unknowns though. T is the same, but the SB and the SA are different. However, we know one's thrown from the top, one's thrown from the bottom. They're going to meet somewhere along this lines, and when they do, wherever they meet, they would have travelled a total distance of 46 meters between them. Because even if this one had travelled 40 meters up, then this one would have travelled 6 meters down. Okay? Because wherever they meet, that distance plus that distance is going to equal 48. So I can say that the two distances, 46, is equal to 46 meters. That now allows me to put these two equations together and have just the one unknown. So now we've got 5t plus a half gt squared plus 18t minus a half gt squared equals to 46. Simplifying this, 18t plus 5t is 23t. Half gt squared minus a half gt squared would cancel out. So that's going to equal 46. So the time equals 2 seconds. Now that I know the time, I can effectively substitute it into either formula. Okay, my B or my A. But I want the distance from point A, where A was thrown. So it makes way more sense to work out SA. If I worked out SB, I'd then need to take that value away from 46. So we have 5t plus a half gt squared. T is 2, so we've got 5 times 2 plus a half g times 2 squared. And that gives me 29.6 meters. And that is my distance from A. Now, a point on accuracy here. If we're using G is 9.8, what we're basically saying is that this is corrected two significant figures, which means that for accuracy, I should really put my answer correct to two significant figures. I shouldn't be marked down in an exam if I didn't and left as 29.6, but just for accuracy, that's what you should really do. I wouldn't worry too much about it, I just want to make a note of it. So, I'll give you a couple of questions to have a go at, and as always, I'll pop the answers up at the end of the video. Now, in this example, we can see it starts at a height of 2.5 meters above the ground, and it's fired upwards, and then comes down and catches it just before it hit the ground. So you can basically assume that it's hit the ground there. And what we need to do is a velocity time graph. So if I think of my velocity time graph, I'm going to be starting with like a velocity of 24 meters per second. And as it rises in the air, it's going to slow down at a constant rate until it hits 0. At which point then it'll start to drop back down to the ground. So we've got exactly the same. These two should be symmetrical to this point. And at this point it will be hitting that kind of 2.5 meters, which is the height of the machine. Obviously, if it drops a little bit further, it's going to go a little bit faster. So that graph will finish a little bit above this 24 here. See, just a bit above. Now, part B, we want to calculate the speed of the ball when Ahmed catches it. So it's quite straightforward, it's quite simple. If I look at this graph on my left here, let's do this in red. At the point of the machine, so back at 2.5 meters, it's going to have a velocity or a speed again of 24, isn't it? So what I want to think of is u being 24 meters per second. Acceleration is g, gravity, because this is heading towards the ground, isn't it? And all we're trying to find is basically the point or the value here. Okay, so we know that that distance is going to be 2.5 meters, and we need to find v. So we got three unknowns and three values that we know, one unknown. So we can do this. We got v, u, a, and s. So v squared equals u squared plus 2as. V squared equals 24 squared plus 2g times my 2.5. That gives me 625. So V is going to be 25 meters per second. Sorry about that, I just realised I've actually worked out C first, read the wrong one. So let's call that C, and then let's work out B down here. Sorry about that. So B is obviously the height. So the starting value again, 24 meters per second. So this is, we think we've got a floor, we've got 2.5 meters, and then it's going to shoot up to a point somewhere up here, which is, what we're initially going to find. At that point, the velocity is going to be 0. Acceleration is going to be gravity. However, as it's acting in the opposite direction we're going, and we want to think about, it'll be minus g, and s is what we're trying to find. So u, v, a, and s. So v squared equals u squared plus 2as. So it's 0 equals 24 squared plus 2gs. but g is a minus, so that is then the same as taking my 2gs to the left hand side and then dividing by it. So 24 squared over 2g. And that gives me 29.4 meters, or 30 meters to two significant figures there. Now that is just the distance above the machine, isn't it? So height above ground is going to be my 29.4 plus my 2.5, and that gives us 31.9 meters. Now just double checking the question, it is actually to the nearest centimeter, so it's actually 31.89 meters to nearest centimeter. C I've already done, as I did the wrong order there. So let's look at D. Calculate the length of time the ball is in the air. Now you could do this in sections. Find the time from here to the top, double it, and then that time at the bottom. Or you should be able to do it in one go. You just need to think about how you're going to set it out. So if I want to think of, say, down being positive, it's going to go up at 24 meters per second, which will be minus 24. The final velocity we know is 25 meters per second, as we found that already. The acceleration is positive g, this is going down, and then t is what we're trying to find. So v equals u plus at, 25 equals minus 24 plus gt. So that gives me 49 equals gt, and 49 divided by 9.8 is 5 seconds. Now, again, you know, like I said, you could do it in sections here. Doing it in sections should pretty much mean you don't need to use some of your worked out values, but it's much quicker to do it in one go, like so. And even if I took up as positive, I will still get the same value. So we go, a car driven along a straight track passes O at time 0, let's call that O, and it starts to decelerate. So that is my direction of A. Car passes point L when t equals 1 and point M when t equals 4. And OL is 54 and L to M is 90. Okay, so we've got quite a bit of information here. So looking between O and L, what do we know? We know the time taken is 1 second, and we know the distance is 54. And between L and M, we know the time taken is 3 seconds, and the distance is 90. What we also know is the speed at L is going to be the same. So for this one, our V and our U are going to be equal. So let's call this V for OL and U for LM, and we'll just make them both equal to V. And then obviously, not time, acceleration is going to be the same for both of them, and that's what we're trying to find. So for the first one, we got S, T, V, and A. So I'm going to use S equals VT minus a half AT squared. So 54 equals VT minus a half AT squared. And T is 1, isn't it? So let's get rid of that. So it's actually going to be V minus a half A. So there is one equation. Now looking at the second one, we know U, A, S and T. So this is S equals UT plus a half AT squared. So again, S is 90. U is this V that we just called it, and T this time is 3. So 3V plus a half A times 9. So here we've got 90 equals 3V plus 9 over 2A. And this is our second equation. Now, we've got two equations, two unknowns, but we actually want to combine the V's together just to find our A. So we want to rearrange. So if I call this 1 and call this one 2, look at from 1, we can say that V equals 54 plus a half A. And then let's sub that in 2. So we've got 90 equals 3 lots of 54 plus a half A plus 9 over 2A. So 90 equals 162 plus 3 over 2A plus 9 over 2A. Taking away 162 gives me minus 72. And 3 over 2 plus 9 over 2 is 12 over 2, or 6A. So A is negative 12 meters per second squared. And that's obviously because I'm taking this way as my positive direction, the direction I'm going in. Another way I could have done this is this distance OL, and then instead of LM, I could have just done OM. I just noticed that afterwards. And that way I could have used the same formula as in like S equals UT plus half AT squared for both. Same value of U. Or an idiot, that would have made a bit more sense. Okay, maybe some of you did it that way, but you should still get the same answer. Now, part B tells us now we've got a new point N. We don't know the time of that, but we know that the velocity is 0 at that point. Find this distance from M to N. So let's do that total distance, ON. And at ON, we don't know what U is, do we? But we know that the distance, well, that total distance is going to be my 144 plus that little s. But we'll just work out that total distance first, and then we'll take away the 144 from it. So the distance I'm trying to find, V I know is 0. A I know is minus 12. So as it stands, I don't have enough information. So I do need to work something out. Now, since we know the acceleration, we can find at least U at the very start. So let's look at OL again. We know the time was 1 second. We now know the acceleration is minus 12. We want to find U. And we know the distance is 54. So S equals UT plus a half AT squared. So 54 equals U plus a half times minus 12 times 1 squared. So we got minus 6 added on. So U equals 60 meters per second. So now this can go up here. So back to ON, we now got U is 60. We got S, which we want to find. V is 0, A is minus 12. So we got V, U, A and S. V squared equals U squared plus 2AS. V is 0. 60 squared plus 2 times negative 12 times S. So we get 24S equals my 60 squared. So S is 150. This is the total distance though. Distance of MN is going to be that 150 minus my 54 plus 90. And that's going to give me 6 meters. And then we're done. So we've got a car and a motorbike at rest adjacent to each other. Adjacent just means next to. Set of traffic lights along a straight stretch of road. Set off the same time at t equals 0. We've got the motorcycle accelerating at 6 meters per second until he hits 30, and the car accelerating uniformly for 9 seconds until she hits 36. Find the acceleration of the car is the first thing, but before I jump into that, let's get all this information down. So this is basically what we know. Now, find the acceleration of the car. We know U, V, T, and we want to find A. So that is V equals U plus AT. So we get 36 equals 0 plus A times 9. 9A equals 36, A equals 4 meters per second squared. Now, for me to find the graph, because we've got to draw a speed time graph, it would be useful if I know how long it takes the bike to get up to speed. So we know U, V, A, and we want to find T. So same formula. We've got 30 equals 0 plus 6t, so t equals 5 seconds. Okay, so that'll make my life a little bit easier. So the bike takes 5 seconds to get to 30. So we're on a line here, and then after that it goes at the same speed, isn't it? Constant velocity. So we can keep that going. Now we want to take a dashed line across, and we also want to take a dashed line down, don't we, to show our time and our velocity at that point. So time is 5 and our velocity is 30. And this is the bike. Now, our car takes longer, doesn't it, to get to 36. 36 isn't much bigger than this, but 9 seconds is almost double the distance. So we want to go somewhere around by here. So again, you know, take my ruler and a pencil. It's going to be kind of almost double the distance in terms of the time. And this will probably be good enough. I mean, it's just a sketch really. Again, dashed line across for my speed, dashed line down for my time. And that is the car. Obviously I've made this quite big. It doesn't really matter, you know, how long I make this part of the graph. But there we have the graph now for part B. Now, for part C, obviously they're level at the start here. The next time they're level is here. Obviously the graph's no good to me in terms of, you know, finding the value. I need to use my formulas, but this is what we're trying to find. The same time when they're level. Okay, so this will be when they essentially have the same distance, isn't it? But obviously we're trying to find the time, but this is the same distance. So first, let's just assume that they're both going to meet somewhere down here at the time t. We don't know where along here they're going to meet. Okay, don't make the mistake of thinking they meet here. That's just when they meet in by a time. It's not when they're actually meeting. Okay, so they're working down there at time t. So let's look at the distance the bike has gone. So the distance of the bike is going to be the area of this triangle. So 5 times 30 over 2 plus the area of this rectangle, which is 30 multiplied by t minus 5. As obviously that length is t minus 5, that height, sorry, the height of the bike here is 30. And simplifying this, we get 75 plus 30t minus 150, or 30t minus 75. Now let's look at the distance the car's gone. So the car's done this triangle here, which is 9 and 36, so 9 times 36 over 2, plus, then it's done this rectangle here. So that's 36 multiplied by t minus 9. Again, let's simplify. And we get 162 plus 36t minus 324, which is 36t minus 162. Now these two distances are equal, aren't they? So that means that 30t, let's do this way, SB equals SC. So 30t minus 75 is equal to 36t minus 162. So 6t is going to be equal to 87. So divided by 6, and we get that the time is 14.5 seconds. Okay, hopefully not too difficult to follow that one. Final question here, question 4. So we got Guy Jim is just up on a cliff. The cliff is 122.5 meters. We got a stone and it's just dropping down. So its initial velocity is 0. And we can ignore air resistance here. So we also know that our acceleration is gravity. And if we take down as positive, it'll be a positive g. Now, since we also know the height, which is 122.5, we can find v, we can find t. So we need to take the time taken first. So remember, we've got u equals a equals g, and s equals 122.5. We want to find t initially, and then part B we'll end up finding v. So part A, we've got u, a, s and t. u, a, s and t. So that is no v. So s equals ut plus a half at squared. S is 122.5. U is 0. Half g t squared there. So t squared is going to be 122.5 divided by a half g, which will give me 25. So t is going to be 5 there, because obviously we're not going to have negative time. Part B, we're going to take the same things and we're obviously finding V in this case. So we've got V, U, A and S. So V squared equals U squared plus 2AS. If you're wondering how quickly or why I'm quickly saying the formulas and spotting them, it's because I write them down all the time. It makes your life so much easier if you just keep writing everything down. So don't take shortcuts when you're revising. So this is 2401, so V is the square root of that, which is 49 meters per second. Oh, they give us nice values for a change. Now, as we go into the question further, it tells us that after 2 seconds, after 2 seconds after the stone begins to fall, Jim throws a tennis ball. The tennis ball's initial speed is U and hits the stone just before they both hit the sea. Well, it doesn't say just before, but before they both hit the sea. Find the minimum value of U. So the minimum value will be the slowest he can throw it, which means that we have to assume it hits the stone pretty much at the instant it hits the sea. So if I'm thinking of now for part C, we know the information of the stone. So I'll put that down here. And that's based on it just about to hit the sea, isn't it? And then if we think of the tennis ball, well, U is U, that's what we're told. A is G. It starts 2 seconds after the stone, so for this one, it must get there in 3 seconds if it's going to hit it just before it enters. Obviously, we don't know V. Oh, and we know the height, don't we? 122.5, because that's got to be the same distance there. Now, since we don't know V and we don't know U, and U we want to find, we're looking at U, A, T and S. So S equals UT plus half AT squared. So 122.5, and that is equal to U times 3 plus a half G times 3 squared. So we got 3U on this side. So 3U equals 78.4. Dividing this by 3, and we get that U is 26 1/3. No, 26.13, and the 3 is currently recurring. So U equals 26.1 meters per second. Hopefully that wasn't too difficult there. Now, part D. If you had taken air resistance into account, what effect would this have had on your answer to part C? So the tennis ball, we can pretty much assume, is bigger than the stone. At least I would have thought so if you just kicked it off the edge. That is probably the assumption I would make. Otherwise, you'd be talking about rock or a boulder if you're talking about bigger things. So we would say that the tennis ball is bigger, so it would experience more air resistance as it's bigger, and it will be moving faster because it covers the same distance in 3 seconds. So that's what we need to say. That means that the real value of U then would be greater than this value of U, because of the air resistance would be slowing it down. So we'd need to start off faster. And there we have it. Hopefully you found this video useful. If you did, don't forget, give us a like, thumbs up, comment down below anything you want to ask, or anything you want to say, and subscribe to the channel if you haven't done so already.